Actually, I'll start off with a story now. I forgot, don't think I told the story back when we were doing adhesive bonding. Did I tell you about the automotive problem of bonding the carpeting to the floor of the automobiles? This course is actually designed to be as simple as possible. I mean, you don't have to do a lot of work, and you get your breakfast taken care of and things like that. But there's various reasons for that. But in addition, I used to teach it for students at a major automotive company, and I used to tell the names of these companies. But I guess since this is all on the web now, I should be a little more careful, a little more discreet. But most people can figure it out anyway. But as a result, and I've also taught parts of this course at companies like John Deere and things like that. But that means that sometimes I get people who don't have college degrees. I've had people with high school educations take this course. And obviously they may not be able to follow some of the things, but hopefully a lot of it's simple enough and they can follow some of the principles. So what happened with this automotive company, you can get a master's degree while you work for this company through Purdue University or Rensselaer Polytechnic. And so I got this course qualified 10 years ago or whatever, so that you could earn credit at one of these other universities. You could pay MIT tuition and you could get credit at the other school, and they would give you a master's degree for this and other courses, obviously. But the problem was, there was an assembly plant in Ohio, I think it was Ohio, where it wasn't one of the exempt employees that wanted to take the course. It was one of the union hourly employees on the assembly floor. And the problem was that the way they structured things in the automotive company is they had this kind of tuition reimbursement for the exempt employees, but not for the union hourly employees. Now, it turned out the guy who wanted to take the course, who was union, actually had a college degree, I think in psychology or philosophy, and he also happened to be the union shop steward. So he was putting a little pressure on the company to let him take this course. And it turns out the engineers at the plant were actually in favor of it, but his immediate supervisor, the tuition was going to have to come out of his budget, and he didn't have a training budget for the hourly employees. You don't care about the union folks in the automotive business. And I will put that on the web because it's true. I mean, you won't find worse management relation. Actually, you can find worse management relation problems, but not that are actively encouraged by the management like the big three automotive companies. They've never gotten the idea that respect your employees and treat them well, and they might do something for you. But nonetheless, I get a call from these engineers saying, we'd like this guy to take the course, but we're getting, our management says he wouldn't be able to take an MIT graduate course. I said, I've had high school students take this course before. They can get something out of it. And they said, well, how can he handle it? I said, why don't you have him call me? So he calls me. So I'm talking to the shop steward on the phone, and I said, and then he was going to want to explain to me the real financial problem with his supervisor didn't want to pay the tuition. And I said, well, you tell your supervisor that if you take this course and you don't save your company at least the tuition out of something you learn in the course, then I'll pay the tuition, okay? I mean, I love to kind of, bet with people and make them shut up, okay? So he went back to his boss and said, okay. So anyway, we're going through the course, and they decided to let him take it. And he calls me up one day when we're doing adhesive bonding, and he says, we've had this big problem where we glue the carpeting down to the steel decking, and we actually have a robot kind of spreading the adhesive, and then people actually put the carpeting down, but the carpeting just doesn't stick. And for 6 months, they've had consultants coming through here, and nobody can figure out the problem. And when you were talking about adhesive bonding, you mentioned that things need to be clean. And I was wondering, we have a water jet cutter over here that is right next to this robot station where they're putting the adhesive that's cutting plastic. And there's always a mist or a cloud of this water and plastic in the air. You think that's having anything to do with the poor adhesive bonding? And I said, yeah, I think it is. So he went out there and he finally got them to put some screens and some vents and stuff to keep the rain from falling on the adhesive bonded areas, and saved them $100,000 a year. Okay, now there's a couple of lessons to that. Is I guess the big lesson is anything you do in the automotive industry is big bucks. Okay, it can be the simplest thing in the world, but there's relatively simple things that can be done. Professor Fine says there are $100 bills lying all over the floors of American factories. If you want to get rich, just go out there and pick them up. And in fact, it's true. I think a lot of people, particularly LFM students, after they've gone out there, realize that it's true. It's amazing what people do or don't do. Anyway, we were talking about brazing. It's more widely applicable than soldering, and it produces higher strength joints. But some of the concerns are if you have volatile alloy additions, they can create problems, either health effect problems, or they can, for the workers, or they can degrade the furnaces or whatever. You have intermetallic compound formation, and thermal stresses. You only have thermal stresses if you're welding or brazing dissimilar materials, like a ceramic to a metal or two different metals that have different coefficients of expansion. If you got the same material on both sides of the joint, it has the same coefficient of expansion, there's no thermal stresses that build up because there's no difference in coefficient of expansion. And you have erosion of the base metal, which can be problems. Now, I mentioned furnace brazing the other day. I really haven't talked about the different types of brazing processes. You have to heat things up. And one thing that they do in large-scale manufacturing is furnace brazing, and you take a part, and it might be a little circular part, and you put a little ring of brazing alloy. You can buy these brazing alloy rings, or they're either stamped out of a piece of sheet metal as a little ring of brazing alloy you slip over the joint where you want it to be, or they make them out of wire and just make a little ring out of it, or other more complex shapes. And you place the brazing alloy, you put the whole thing in a furnace, and you bake it for an hour or whatever. The furnace has to have good atmosphere control. Sometimes you put hydrogen in there as the fluxing agent. But anyways, you're usually doing that when you have large numbers of parts. Another way to do it, if anybody in here ever done any brazing themselves or silver soldering? I mean, just one? Okay. Two? Okay, so some people have done soldering. How many people have done soldering, soft soldering? Okay, most of you have done soft soldering. Well, brazing is just a little bit higher temperature. And you can obviously use a torch to do that. And industrially, when you have a smaller number of parts than a big furnace batch loads, they basically have little lazy Susan tables, and they'll have torches sitting at a station, and they'll have a lazy Susan, and the part will come in, and someone might put it into a fixture, and then the table rotates, and there'll be a preheating flame, and then they'll rotate to the next station, and they might have another person put a little piece of solder on there, or brazed alloy on there, and then it goes to a next station, and that just adds more heat, and it melts and flows, and then someone else takes it off. So sometimes it's people, sometimes it's robots, but you can do torch brazing, you can do furnace brazing, and there are actually dozens of others. You can do induction heating, virtually anything. You can do resistance brazing, where you just pass a current through the metal to heat it up and cause the whole thing to braze. Virtually any way you can think of to heat a metal is used by various people to do different types of brazing. And different types of heating can produce beneficial properties in certain cases. For example, if you do induction heating is a process where you have a magnetic coil that goes around the part. So if I've got a part here that I want to produce a braze joint, and I put it inside some magnetic coils, so these are coils going around in a circle around this thing, and I put an alternating magnetic field on this, typically on the order of 100,000 hertz. the oscillating magnetic field will induce, that's why we call it induction, induce a current, eddy currents, in the metal. So you have this oscillating magnetic field in the presence of a conductor is going to generate currents. The currents in here resistively heat the metal. Except they do preferential resistive heating on the outside surface of the metal rather than in the very center. And so sometimes you might use induction heating because you want to induce greater heating on the outside rather than the inside for some reason on your part to get control the way the braze flows or whatever. In fact, one time we were worrying about brazing porous graphite, and the porous graphite were essentially tubes, and they used it for filtering, and very, very fine filters in these graphite composites. They would start out with a plastic cloth and weave it together and then wrap the cloth into a circle and then put it in a furnace and bake off all the stuff and graphitize this polyacrylonitrile plastic and end up with a porous graphite substrate. And then they do some other things to control the pore size so that you'd have a filter and you could pump a fluid in one side and get your solid particles go out with your influence stream and get the clear liquid come through the pores. Well, they wanted us to braze this tube, and it turns out that we ran into a problem. When we first tried to braze it, we found nickel alloys that would wet the carbon. Nickel likes to wet carbon pretty well and doesn't react with it to dissolve it. It's one of the few metals that doesn't in the transition metals that doesn't dissolve carbon. But the problem was with all these little pores, the surface tension of each one of those little pores was acting like or the liquid nickel was acting like the carbon was acting like a sponge to suck up all the liquid. And instead of just heating down here and forming our little seal that we wanted to form, we actually were forming, nickel was going all the way up in, and we were wicking away all of the braze alloy. It was just being soaked up into the porous carbon like a sponge and leaving nothing for the joint. Now it turns out in soldering you can buy desoldering tools, which are little wicks, and they're nothing more than a collection of little fibers that have some flux on them, and the solder wants to flow in that, and because of the very small cross-section between the little fibers, the surface tension, which goes as 1 over R, or the surface tension force goes as 1 over R, will suck up into that little fibrous wick, and you'll pull the solder right away from the joint. So if you're trying to desolder a joint, you have these little wicks. Well, we basically had a porous carbon wick for our solder, and the engineer working on it came in and showed me. I thought, oh gee, I should have thought about that ahead of time. I didn't think about it, and he had already figured out the solution. The solution was to braze in a temperature gradient. If you braze in a temperature gradient and it's hotter down here than it is up there, then the nickel's not going to flow up there. It's going to stop because it runs out of, it's going to solidify, right? So we were able to make the joints we wanted to make even in the porous carbon by doing it in a temperature gradient. And essentially we went to induction brazing and just heated up the bottom here and not the top. Before we were heating the whole thing with a great big flame, and we were getting everything fairly uniform and hot, which was not what we needed in that particular case. So virtually any process you can think of or of heating materials is probably used by someone somewhere as heat for brazing. This is the sheet from yesterday, which has all these other summary things. And vacuum brazing actually is the problem with a vacuum furnace is you add about 50% to the price per hour of your furnace compared to an air furnace. So I would say vacuum brazing is probably less than 10% of all the brazing that's done. Most of it's done in a simple hydrogen atmosphere. Anybody know what the typical hydrogen atmosphere in industry is? It's not actually hydrogen. They use a safer material that ends up producing hydrogen. But to transport it, you don't want to be carrying hydrogen all over the country because it's a gas and you have to put it in high pressure cylinders and stuff. you'd much rather transport hydrogen as a liquid, but to do that, it has to be really, really cold. Anybody know what they use for furnaces? Pardon me? Ammonia, yep. What they call cracked ammonia. They transport ammonia, liquid, which is like only minus 30 degrees centigrade, but ammonia is NH4, or NH3, sorry, ammonia, the ion is NH4, but it's NH3, and if you put it through a little arc discharge, you can decompose it into hydrogen and nitrogen, and you can buy a nice little system that is fairly compact, and you feed your ammonia into this little cracker, which just uses a little electrical energy to crack the ammonia, and you get hydrogen and nitrogen out, which is a perfect gas for most types of metals for heat treating them. So more often than hydrogen, they use cracked ammonia industrially just for the safety factor. That's not to say that ammonia can't burn and explode. It can, but its flammability limits are much tighter. And we'll talk about that when we get to flames next week. Other questions? We then started talking at the very end of the day yesterday about the effective joint thickness. And we'd mentioned that back with adhesive bonds. As you get to thinner and thinner joints, the strength goes up. And it's called contact strengthening. And here's the differential equation that I promised we'd solve. If I have two pieces of base material and I have an inner layer in between of height h, and I look at a little volume element, I pull this thing in tension and look at a little volume element, so I take the volume element out of here and I write down the forces that are on this thing when I pull it in tension. Well, sigma yy is the tensile force I'm applying, or tensile stress I'm applying. The whole thing has a width of dx. That dx is supposed to be the width of the whole thing here, not just a portion of it. So it's the width of the whole thing. I have a shear stress here. The material, think of this, if this is a viscous fluid and I was pulling it apart, the stuff would start to neck down here and suck in as I create more thickness to it, right? So it would pull in from the sides. So there is a shear stress. If the volume element is over on this side, or the left-hand side, your right-hand side, but yeah, your left-hand side, okay. It's your left-hand side too. So over on the left-hand side, the shear stress is in this direction. So there's a shear stress which is proportional to sigma yy, and it acts over an area dx. This is unit thickness into the board, and it's proportional, and eta is just the proportionality constant, whatever that is. There is also, it turns out, there's no stress on the material, the little volume element out of here at the end. That's the one that sucks in. But in fact, that one is going to push, as it sucks in, it's going to push against the volume element here, and both of those are going to push against the third one in, and all three of those will push against the next one. So it turns out I have a varying sigma xx stress as this material tries to suck in as I'm pulling up this way. It's kind of Poisson's ratio effect on the braze alloy here, which is softer than the base materials. So sigma xx times the height h, that's the area, is equal to sigma xx plus d sigma xx, which is whatever the variation is on this thing. And now if I resolve the forces in the x direction, I end up with the difference here between these two is just d sigma xx h, because the sigma xx's cancel out. It's their opposite direction. This sigma xx is to the left and this one's to the right, so those two cancel out, and I just left with d sigma xx h must be balanced by the shear stresses, which are 2 eta sigma yy dx. And if these are principal stresses, and they're not exactly principal stresses, but they're pretty close, it turns out d sigma xx for a principal stress is equal to d sigma yy, so I can change this d sigma xx to a d sigma yy, and with that little prestidigitation, actually, I end up with a solution to the differential equation of sigma yy over twice the shear stress of the material, which is the shear stress along here, or actually the shear stress of the braze alloy, is equal to an exponential 2 eta x over h, for whatever that's worth. The only reason I prove that one is because you won't find it in a book. Actually, you will find it in a book, but a different type of book on deformation. and in compression rather than tension. But in any case, if you really want to know physically what's going on, now that we just solved a differential equation to prove this in an MIT course, right? If you want to know what's going on, if you know, how many people know what Moore's circle is? So, okay, the majority of you. If you haven't heard about Moore's circle, don't worry about it. But Moore's circle is where you plot the shear stresses on the vertical axis versus the principal stresses on the horizontal axis. And it turns out you get a circle of stress here that represents all the different orientations. So if you want to transform your coordinate system to something slightly different, if you have some angle theta here, or actually this would be 2 theta. If you transform by theta, then this angle represents 2 theta, and we don't have to get into all that. But basically, there is some shear stress of the material, tau y. That's the shear stress of the braze alloy. If we were talking about the silver joints, that's the shear stress of the silver. If the silver has a tensile strength of 10,000 psi, the shear stress is about 5,000 psi. And it's not going to be any greater than that, because how can it get stronger? The silver doesn't get any stronger. And so right here on the edge where the stuff is not constrained, that silver will start to yield at 5,000 psi shear stress. And this is what the Moore circle looks like. This would be Poisson's ratio times sigma yy, and that's just sigma x. Sigma xx is Poisson's ratio times sigma yy. And there's the Moore circle. However, as you start marching in towards the center, the Moore circle, which doesn't change in diameter, starts marching out this way. And the reason is I end up getting triaxial stresses. Here, I simply have biaxial stresses. There's no stress at the surface. But as I get in here, I'm squeezed from all directions. Actually, I'm pulled from all directions in this case. It's a tensile triaxial stress. And what happens is you have a yield stress of 2 tau y in tension, which is this level right here, but the exponential we're talking about adds a triaxial stress on top of this that looks like this. And as you go in further and further towards the center, the Moore circle moves further and further out with a hydrostatic tension in the braze alloy. Now, it turns out if a material is under hydrostatic compression or tension, it doesn't yield, because a metal yields by shearing along its shear planes, and a hydrostatic stress doesn't produce any shear. There's absolutely no shear. I mean, shear is on the horizontal axis. I'm sorry, shear is on the vertical axis. The principal stresses, or the hydrostatic stresses, are where the shear stresses are 0. So this is the hydrostatic component along this horizontal axis. And as I go in towards the center, I get a larger and larger hydrostatic stress, or sometimes it's called a triaxial stress. I have a very high triaxial stress in the center of this joint. It decreases over towards the edge. And that gives me an actual local yield strength of the soft material that goes like this, not like that. So if I have, and it turns out that the proportionality is exponential of x over h. Okay, exponential of x, and it's got this x over h, which is a width to thickness ratio. The thinner the value of h, the greater the strength of this joint. The higher this hill of triaxial stress is, and the actual yield strength of the material is not this value, but it's the average value across this whole thing. And so it turns out you get what's called contact strengthening. Physically, all it means is the material in the very thin joint can't yield because it's constrained by the non-yielding material, base material on either side. And it gives you a contact strengthening. Well, that contact strengthening, when you're dealing with a very soft material like silver that yields this particular stuff, they said it yielded at 15,000 psi, you could get with a joint that's on the order of 1/10 of a thousandth thick. If it's a perfect joint with no defects in it, you could get a strength of over 100,000 psi. Effective strength in tension. So you essentially have a joint that acts like it's much stronger than it really is. And that applies to adhesive bonding, it applies to brazing, it applies to soldering, but it doesn't apply to soldering quite so much, because the problem with soldering is actually the question Chris asked yesterday or the day before. What happens if you get creep? If you get creep, then the hydrostatic stress can relax over time, and the material in here can start to flow in a viscous way, and that viscous flow is going to relieve the hydrostatic stress, and you're going to lose your strength. So you don't get contact strengthening unless the material essentially is not in the creep regime. But for brazing, we're not in the creep regime, and so we actually do see significant contact strengthening in braze joints. As braze joints get thinner, they essentially get stronger. Yep. Well, in torsion or shear, and torsion is a form of shear. Shear is also this way, if you take two rods this way, but you can also twist them. You don't get increased strength in shear because there is no hydrostatic stress component if you go through that, okay? The silver layer or the soft braze layer is going to be in shear everywhere, and there's no hydrostatic component. The hydrostatic component comes from this Poisson's ratio effect of pulling the material in tension. So the contact strengthening doesn't work in shear, but it does work in tension. Now, a lot of times your joints are not nice, simple, planar joints, and so if you may not be getting, if it's a right angle joint, you may not be getting contact strengthening in one direction, but you'd be getting it in another direction. And so effectively, complex braze joints do behave stronger in simple tension or relatively simple loading conditions. They act much stronger than you would think from the strength of the braze alloy. The other problem is they're not better in creep, but they're also not better in fatigue, because fatigue is a slow crack growth where the crack progresses across there very slowly, and essentially as the crack starts from the edge and progresses across, it's relieving the stresses, and the tip of the crack is always the tip of the crack is not in that triaxial stress state. Nonetheless, for simple loading conditions, most braze joints have a fair amount of contact strengthening and are therefore somewhat surprisingly strong. Now, if we go back to the thermal stress problem, I'm going to change topics here and go back to thermal stresses. Another problem because of thermal stresses, most braze joints cannot be made in a dimension greater than about a centimeter. Remember when we were talking about the semiconductor chips, and they can't bond them to the substrate over a distance greater than about 1 centimeter? And that's because the thermal stresses in the semiconductors build up and go as one more dimension than the area that you increase. So your ability to carry stress goes up as r squared, but your ability or your strain energy goes up as r cubed, and therefore as your joint that you're bonding gets larger and larger, the total thermal stress or thermal strain to strength ratio is going down. Okay, or actually the thermal stress to strength ratio is going up, and your strength is going to go down. And typically, for both bonding silicon and maybe soldering silicon to its substrate, and the types of temperatures you're going to get in the operation there, and you got a temperature gradient when you're operating a silicon chip, those temperature differences mean that you really can't bond silicon chips or gallium arsenide chips with an area greater than about 1 square centimeter. It turns out for braze joints, if I'm going to braze two dissimilar materials with a thermal coefficient of expansion difference of about 10 to the minus 5, which is typical for a metal to a ceramic, you also can't go about more than 1 centimeter in size. If you try to go 2 or 3 inches in size, you can make a braze joint, but as soon as the thing cools down, the thermal stresses are going to typically crack that ceramic. And even if they don't crack the ceramic, the residual stresses are going to be in addition, and you put it in service, and the actual effective strength is much, much less because of the residual stresses that are locked into that joint. So that problem being fairly common, if I go and I went back a few years and looked at cutting tools in a machine, if you go to look at tools, the cutting tools on a lathe, on a milling machine, There's been a tremendous change over the last 25 years in that. When I was a student working on a lathe, we would typically just have a piece of hardened steel that you take over to a grinder. So you got this little kind of 3/8 inch, well, they came in different sizes, piece of steel, and you grind a tip on the end. So here's your sharp tip on the end, and you would cut with that, and you clamp the whole thing down here. And this is just a piece of hardened steel. Well, it turns out there's a lot of friction when you're cutting on that tip, and the steel will get hot enough. In fact, tip temperatures, if you go fast enough, you can melt the tip of the steel. You can generate enough friction at the tip to melt that. My wife used to get upset when I was a graduate student, because I'd always throw these tools in my pocket, and the sharp tips would always put holes in my pockets after a couple of weeks. But anyway, that's what we used. And so 30 years ago, when I was a graduate student, they were starting to use insert tools where they had ceramic, or actually had metal inserts or ceramic inserts, whereas a similar type of tool post, but on the end, they basically just had a little ledge, and they would braze a piece of carbide. Well, that piece of carbide can never be more than about 1 centimeter in cross section. Okay? They could braze it, and you can get braze joint strengths of 40,000 psi. And so the carbide's much harder, higher melting temperature, and you could machine maybe 2 or 3 times as fast. And then they were starting to come out with ceramics. But the ceramics, they never tried to braze. Actually, they probably did try to braze them and found out that there's too much residual stress and the ceramics would crack. They basically built a little thing up here with a little screw through it, and you basically would hold it down in a little vise. You'd hold the ceramic in a vise. And so instead of a carbide, they started out, they had aluminum oxide, and then they get to all kinds of fancy ceramics now. And what's happened is the cutting speed in the last 30 years on machine tools has increased by probably a factor of 30 to 40 times because of this. If I could go at 100 surface feet per minute here, I might be able to go to 3,000 surface feet per minute now with the fancy ceramics. And that has had a tremendous effect with numerical controlled machine tools in terms of reducing the cost of lots of things that are complex parts that we have to machine. Now, it turns out that the big driving force for that, turns out, was the U.S. Air Force. And the problem was, remember the buy-to-fly ratio in 3371? I talked about the buy-to-fly ratio. You make a forging, and the forging back in the 1970s, the forging might weigh 20, 30 times as much as the final part you're going to end up machining. And so you're machining away 95, 97% of your material you're turning into chips. And so you've got this titanium alloy or nickel-based superalloy that you're paying $30 a pound for, but you're going to take, for every pound you put in the aircraft, you're going to throw away 30 pounds of chips. Now, the chips might still be worth $10 or $15 a pound, but let's say I lost half the value. If I'm throwing away 29 pounds of chips for every pound of aircraft weight, that $30 pound part actually cost me $1,000 a pound in terms of chips, of which I only got a credit back of $500. So actually I'm paying $500 a pound for a $30 a pound material because of all the machining. So the Air Force, back in the late 60s, early 70s, went on a big near-net shape manufacturing project. So they got the forgings more precise so that you didn't have to machine as many chips. They went to all kinds of fancy things, and we talked about some of that in 3371. But they also spent a lot of money coming up with better machining tools that could go faster and faster. Let's face it, if the same machine tool, which cost you, well, actually, the machine tools in the old days might cost you $100,000 because the spindle rotated at, 1,500 RPM because you only wanted 100 surface feet per minute. But Today, they have that same machine tool may cost you $500,000 or $1 million because the spindles are now rotating at 10 or 15,000 RPM. Okay, how high? 30,000, 40,000 in some cases.
8,000 feet a minute in rapid.
Right. Okay. So in any case, if you go into a shop. In fact, last week I was in a shop where they make aluminum propeller blades. Okay. There's only two big companies in the country, and one of them has the small aircraft market, and the other one has the big aircraft market, and they were kind of overlap in the middle. I was in the small aircraft plant last week, and they had this old machine that could do 2 propellers at a time, and it has a numerical controlled machine tool, and of course the propellers have this complex shape, and so the tool was multi-axis, and the tool could rotate, the part could rotate, and the computer was controlling it to give you the contour you wanted for your propeller. That was the machine, which was a machine of almost the size of this room, well, half the size of this room, that could do 2 propeller blades at a time. And I suspect that machine, which was probably 30 or 40 years old, probably cost $500,000 in its day. Then they had about 20 machines, which were newer machines, which were much more compact. They could do 1 propeller blade at a time. They took about 1/10 the floor space to operate. So now you've got a 5-fold improvement in your floor space operation because you got a big machine that does 2 propellers, and then you got a small machine that can only do 1 propeller, but it takes 1/10 the space. So you've got a 5-fold improvement in reducing the real estate you need on your plant floor. And basically the operator just puts the 1 propeller in there, closes the door. The other one, they didn't have a door. They basically just had, the lubricant. They had curtains there to try to keep the mist all in that corner of the plant on the old machine. The new machines were completely enclosed, and you drop the cover. A beautiful, nice clean plant around the new machines. And the new machines were much more accurate than the old machine. And they also, the spindles went much faster and turned out parts probably quite a bit quicker. I suspect that the old machine may have they probably were doing their largest propellers on the old machine. If you go there 5 years from now or 3 years from now, the old machine will probably be scrapped as they get some newer machines. But most machine shops you go through right now, you can see this kind of gradation from 30-year-old tools to modern tools. However, those little tools today probably cost $300,000 or $400,000. I mean, may only be a little bit bigger than 3 times the size of a desk in terms of floor space, but it is considerably more expensive because of the faster spindles and everything else. But they had to change the bonding technology, and in fact, they still are basically just screwing and clamping down these ceramic inserts because you can't braze them. They'd love to braze some of these types of things because braze joints are potentially stronger except for the thermal stresses, which are going to, in a highly loaded application like that, are going to cause failure fairly rapidly. So if you got a solution. Now, well, actually, there is a solution. The solution, if I wanted to bond more than 1 square centimeter, I actually have to go to patterned interlayers. So if I've got a big surface of some metal, and I want to put a ceramic on top of it, I can't bond the whole surface, so I basically have to either cut out the metal or cut out the ceramic and essentially only bond half the surface. Okay? So I'm only going to bond here, and these spaces are voids. I basically put grooves in the surface, and now the whole thing can expand and contract between those. The residual stress builds up based on that distance cubed. The strength goes as r squared. The residual stress goes as r cubed. And so I'm going to keep all r small, but I'm going to have a bunch of them. And in fact, that principle of kind of separating things applies to all kinds of things. It applies when I'm doing solder ball bonding with printed circuits. or well, yeah, printed circuits, or in semiconductor bonding. Remember the ball grid array or the flip chip C4 technology. Essentially, the reason you can bond over a 2-inch area on something like that is because I've got a pattern interface. I'm not bonding the whole surface. I've got 400 balls or 1,000 balls, and each one of those has their own little residual stress, but the spaces in between relax things. You need a very compliant material. What's more compliant than air? Okay, so that's how you relieve the stresses. Remember the fiberware pot I brought in to illustrate the adhesive bonding of, you make the porous substrate and then impregnate with the Teflon. The bottom of that pot, or if you go get Revereware, they have an aluminum bottom to the stainless steel pot. And that's basically cold bonded, and there's not any significant shear. They're not doing a friction weld to get a lot of shear. They basically sand the surface of the stainless steel to clean it. They sand the surface of the aluminum. They heat up the aluminum. They put the pot upside down on this anvil, and a guy takes the disc of aluminum that you want to bond out of this furnace that's heating it to soften it, so it's not cold bonding, but it's warm bonding, and they put it on top of this thing, and this press comes down and goes wham! Just a straight normal compression, no shear. Now I'm now bonding aluminum to steel, warm bonding where the aluminum is soft enough to plastically flow. I mean, it's kind of a coining operation rather than straight compression. Coining, remember, is the kind of embossing of the details in a coin on the surface. So you're not changing the shape of the disc, but you're deforming it heavily enough that you actually are getting local deformation on the surface. So this is sort of a coining operation, but there's no significant shear. And I remember when I first saw that, I thought, boy, this just doesn't follow the right principles. You're going to get a lousy bond. And in fact, they showed me when they tear some of these bonds apart, you could see it was like 70% unbonded area, just like we learned in cold welding. If you don't have shear, you're not going to get more than about 1/3 contact area, even in a coining operation. So what I told you those first few classes is true. And I thought, boy, this is a problem. And they were telling me how sometimes they have some problems. Might be a high humidity day or something, and they couldn't get good bonds. And these things were failing their tests and whatnot. And I thought, boy, well, we could put essentially a braze alloy and kind of braze the surface or something, or make a transient liquid phase diffusion bond. And then I realized, before I actually told them to do that, that would be the worst thing they could do. Okay? And the reason that would be the worst thing is because if they actually had 100% bonded area over a cross section like that, I mentioned before, if you heated up that dissimilar metal part, aluminum and steel, it's just going to bow on you, and now your pot's going to rock on the stove. Someone's going to spill something on you, and some hot liquid on themselves, and because your pot was not flat on the bottom, they're going to sue you, and they're going to win because it'd be a lousy design. So what they wanted was 2/3 voids and 30% bonded area on those aluminum to steel pots. They didn't want 100% bonded area. They really needed the compliance of essentially a pattern interlayer. It wasn't really a pattern interlayer, but if you cross-section these things, they were defective joints. They were full of pores. But if they didn't have those pores, when the thing heated up, it would distort on you. With those pores, you basically kept the distortion down. And the problem was, sometimes they were getting 30% bonded area, and sometimes they were getting 10% bonded area, and 10 wasn't good enough. 30 was, but 10 wasn't good enough. But 50 or 70 would probably be worse again for that particular application, because you needed a pattern interlayer. Okay? Any questions on any of that? No? Don't know if I got another story in the next 5 minutes. I have to think. May have to start a new topic. Any other pattern interlayer stories? Not that I can tell you without getting myself in trouble. I signed a confidentiality once, but I mean, pattern interlayers are important. So we'll start a new topic briefly. Tomorrow you're going to see what is actually a very good video from 1980. It's called What Happens in High Energy Density Beam Welding Cutting. And we're going to start talking about fusion welding now. And you've got a copy of this in your handout, but we're going to look at the heat intensity on a surface in watts per square centimeter from 1,000 watts per square centimeter to 1,000,000 watts per square centimeter. And on Friday, I'll explain why that's important. But let me explain a little bit about this video tomorrow. It won the prize as the best film at the 1980 International Institute of Welding show. You don't attend those? Okay. But in fact, it probably should win the best welding video for the whole last century. Actually, I hadn't thought that was so funny, but in any case, I mean, it's sort of an honor for them. But anyway, the Japanese put this together at Osaka University, and it's narrated in a nice British accent. The Japanese like British accents. But it is an excellent video. They do things with lasers and electron beam so you can see the fluid flow that's going on. In laser and electron beam, you get a very deep weld pool. You have something on the order of 1,000,000 watts per square centimeter, and you will get, in cross-section, looking at the finished weld, you can get something that's 5 or 10 times as deep as it is wide. Okay, an aspect ratio, so the weld bead looks something like this. And it does that looking on sideways view. This is your weld metal that's solidified down here. This is the material you're traveling in that direction. And the beam actually drills a hole in the material. And you have fluid flow that sweeps around. So you're melting the front wall as you're moving forward with the beam. And the fluid flows around and solidifies in the back. Well, as it does that, it creates certain types of defects if you're not careful back here, depending on the fluid flow. I like to liken it to a motorboat going through the water. If you've ever done water skiing and stuff, you know as you go faster and the boat starts plowing through the water, you get a wake in the back of the boat where you have depressions and you have humps. Well, you're going to see the same types of humps in the electron beam welds, and they'll show you those, okay? In addition, so you can see what happens in laser welding, which is a similar process, and they take high-speed movies, they laser weld on Pyrex glass. So you just look right through the glass and you see the molten zone. You can see the fluid flow. So you probably haven't, I mean, now this movie actually, even though it was maybe a small community that looked at it, this movie has got some interesting things that even people who aren't interested in welding might be interested in. And in the electron beam, what they do is they weld on aluminum with an electron beam, and they use the X-rays that are generated by this 100 kilovolt electron beam that go through the aluminum, and they basically take an X-ray, a high-speed X-ray picture. And so you'll see, you have to look carefully, you're going to have to close the shades. Actually, you'll just see kind of a lot of gray, but you'll see a slightly different color gray in the beam hole region, and you'll see the beam bouncing around, and the bouncing around of the beam relates to some of the defects. One thing they don't explain in the movie is every now and then you'll see a little black dot right in front of this thing, and it welds over the black dot. And when it welds over the black dot, you see black swirl inside the aluminum. That is a piece of copper. They drilled a hole and put a little copper wire in there, and they weld over the copper wire. Copper, being more X-ray dense than the aluminum, shows up black on the X-ray image. And when you melt the copper with the aluminum, it mixes with the aluminum, and you can see the swirling pattern as the copper mixes in on the aluminum. So you need to, they don't tell you to look for that, but that's what they're doing. But that's, I think it's better than my lectures anyway, to watch that movie. But, you know, so that